All right, so what we're going to be thinking about today is the hat check problem. So suppose you have 4 people who come up to a venue and they want to check their hats when they get there. Okay, so here's the hat check guy. And so the pink guy comes up and checks his hat. And the green guy comes up and checks her hat. Yellow checks his hat. Orange checks his hat. Okay? And now they watch their play, they do their show or whatever they do. And now the hat check guy is going to give them back their hats. And the question is, in how many ways can the hat check guy do this so that nobody gets his own hat back? So here's one way that nobody could get their own hat back. So now everybody's mixed up. And so this is the question. In how many ways, or we could turn this into a probability because this is a permutation problem, but let's stick with this. So in how many ways can n people be given back in hats such that no one gets his own hat back? So this is a counting problem, and when we're going to do this, we always want to start by doing some simple cases. So what happens if n equals 1? Well, in this case, we've only got the, let's say, the orange guy, and he has his hat. There's only one hat, and there's only one person, so there's really no way to screw this up. So we're going to say in this case that d sub 1 equals 0. And what happens when n equals 2? Let's see if we get some action here. So now the green guy and the orange guy both come, and how can we screw up their hats? Well, that's the only way we could do it. So d of 2 is equal to 1. There's one way to screw up 2 people's hats. What about d of 3? So now the pink one comes, and we can ask ourselves, how many ways can we screw up these hats? So this isn't a screw up because pink gets his own hat. But if I do it this way, then, okay, that's one way I could do it. Okay, so maybe we should write this down. So we'll draw the orange guy, the pink guy, and the green guy. And now we can ask, okay, how can we screw this up? How many ways can we do it? And let's try to keep track of how many we're getting. So one way to do it is to, if we put the orange here, then we're gonna have to put the green here and the pink here, because if we switch these two, then that's not gonna work. So there's one way to do it. What's a different way we could do it? Well, if we do the orange here, we saw we were kind of fixed. So let's put the orange in the only other place the orange can go. And now where can the pink go? Well, we can put the pink here, and then we're screwed because the green has to go with green. So we could put the pink here and the green here. So this is it. These are our 2 ways that we could do it. So now we get D3 is equal to 2. And what about D4? Well, I do have 4 people, but that's going to get a little tedious. So let's start thinking about it in terms of permutations. So now we're thinking about it as permutations, and we want to say, all right, for our hat checks, how many ways can we write down a word so that no one gets his own number? So here we've got the numbers 1 to 4. I can't put a 1 here, but I could put anything else. So let's put a 2. And now I could put a 1 here, and then I better put a 4 and a 3, and now it's fixed, okay? What else could I do? If I put a 2 here, I chose a 1 this time. What if we choose a 3 this time? I've still got 1 and 4 as candidates, so I can't put the 4 here, so the 4 better go there, and here's the 1. Okay, and that was the only way to do it. So 2, 4, what if I do the 4 here? Now I've got 1 and 3 left. Well, the 3 can't go here. The 3 has to go here, so this is the 1. So we're doing pretty good. It looks like we're gonna get quite a few this time. These are all the ones that start with 2. What about if we start with a 3? So the first letter is 3. Let's like the next one be 1. That's a legitimate thing for the next thing to be. And now what do we got? We got 2 and 4. The 4 can't go here, so the 4 is gonna have to go here, and the 2 will go there. And what about next? We're gonna have 3. We can't put a 2 here, and we can't put a 3 there because we're already stuck with that, but we could put a 4. We have 1 and 2 left, and they can actually go in either order. Doesn't matter in the least. So we got those 2 options. And what next? You might be noticing some symmetry to this problem, which is great. So we'll start with a 4. We can put a 1 next. Now we have a 2 and a 3. 3 can't go here, so 3 is gonna go there. That was the only way we could do that. We can't put a 2 here, but we could put a 3 here. And then, of course, we can put the 1 and the 2 in either order. So based on all of this, we discover what is the fourth derangement number. And now we might think, okay, is there some kind of pattern that I'm seeing here? Well, the things that you want to start looking for, instead of trying to jump to a formula, do two things. Say, okay, is there, the way I've generated these, is there a recurrence relation? Is there some way I can think about writing this derangement number in terms of smaller derangement numbers and see what kind of progress you can make from that? Usually recurrence relations are easier than getting formulas, so we'll deal with the recurrence next time, and the formula will be the last video.